Alright, hello and welcome to lesson 4.4, which is collisions in one dimension. This lesson is basically a part 2 of lesson 4.3, which was conservation of linear momentum. So what we'll do in this lesson is take the conservation of momentum and come up with 3 more specific equations, 3 cases in which it can be used. So this is what we came up with in 4.3. That's the conservation of linear momentum. It states that the sum of final momentums in a system is equal to the sum of initial momentums in that same system. I'm going to take this and expand it out a little bit. First thing we'll do is express this with each object. So usually we use 2 objects in our problems. Let me change that here. Usually we do 2 objects, so I'm going to express that as such. So P1F plus P2F is another way to write the sum of the final momentums. Similar logic here will give us P1O plus P2O. So we have a little more detailed version, but this is still not very detailed. Still pretty general. So we'll plug in M and V to each of these. So P1 final, the final momentum of object 1 will be the mass of object 1 times the final velocity of object 1. Final momentum of object 2 will be the mass of object 2 times the final velocity of object 2. And the right-hand side will be quite similar, except the F's will be zeros. M1V1O plus M2V2O. So this is the most detailed version of the equation that we've seen. And we're going to take this equation and apply it to 3 scenarios. The first is what I'll call case 1. So case 1 is a collision scenario in which the 2 objects are separate before and after the collision. The 2 objects are separate before and after the collision. Here's what that might look like. Maybe it's 2 billiard balls striking one another, moving inward at first, they collide, and they move in opposite directions. So this motion scenario can be described with exactly that we have up here. That is M1V1F plus M2V2F is equal to M1V1 initial plus M2V2 initial. Now this equation will not be provided for you. You either have to start here and derive this yourself, or you can refer to your notes. If you have any situation where the objects are separate at the end and at the beginning, then you can use this equation. Plug in your numbers and solve. Of course, this one's pretty simple. I just took it from here and wrote it down, but we'll see a little more complication as we go on to the next 2 cases. So case 2. This one's a little different. In this case, the objects are separate before the collision, but they are adjoined. They are together after the collision. The 2 objects are separate before the collision, but together after the collision. In other words, they stick together. You could also say that they are adjoined. A-D-J-O-I-N-E-D. Two objects are separate before they collide, but they are together after they collide. So this would be maybe a parent is walking and they catch up to their child who is also walking. They lift up the child and they keep walking. So the child and the parent are separate objects at first, moving in the same direction. Then the parent will pick them up and they move as one with the same velocity. The case we'll draw here is a car hitting a garbage can. So we've got a beautiful car. My cars always look like top hats for some reason. We've got a car moving to the right. I also have a garbage can on wheels, which is moving a little bit slower. So the car catches up, and the car will smash into the garbage can. Of course, later on, the garbage can will probably roll, but if we stop the problem right here, they are one for at least a moment. So the car going really fast will smash it against the car and they'll move on together. So this is called an inelastic collision. In this case, the important thing to realize is that the final velocities are the same for each of these objects. So the final velocity of the car, v1 final, is equal to the final velocity of the garbage can, which is v2 final, so we can just write it as v final. They're both going to move to the right with a velocity of 8 meters per second or 20 meters per second, whatever it may be. The car is smashing this thing, so they're stuck together and they move as one. So let's take that detailed equation that we came up with at the beginning, m1 v1 final plus m2 v2 final equals m1 v1 initial plus m2 v2 initial. Again, that's m1 v1 final plus m2 v2 final equals m1 v1 initial plus m2 v2 initial. Point is, these final velocities are the same, and so they can factor out. We'll just call them v final, and we're left with m1 plus m2 in parentheses. I prefer to write the velocity on the left, so m1 plus m2 in parentheses. They're being multiplied by vf, and the right-hand side remains unchanged. So I think this is a good spot to reestablish the point of this lesson. The point is, there's going to be three types of collisions, and rather than going here and deriving the equation and then figuring out if this one still works, you can just jump straight to here. I won't provide this equation, but it's in your notes now, so you can jump to it. So when two things stick together and continue on as one, you can use this equation, plug in the numbers, and it should be able to solve. Last case we're going to look at is sort of the opposite of case 2. So case 3 is two objects that begin together, but they separate due to an internal force. Here it is. The two objects begin together, but they separate due to an internal force. We saw this in 4.3 with two ice skaters pushing off of one another. here we'll look at our collision carts lab. In the collision carts lab, we had a red cart and a blue cart. We could throw some masses on them. I forget which one was on which side, but it doesn't really matter here. One of the features of that application is you can put a bomb in between these two carts. So in this case, the two carts start at rest. The bomb goes off and it pushes both of these in separate directions. Technically, that explosion is an external force, but as long as it pushes these with the same amount of force as each other, that external force will cancel itself out. So there's an external force to the right, there's an external force to the left, but as long as those are equal, conservation of momentum still holds. Here's what that might look like. The situation here is quite similar to this, but instead of the final velocities being the same, the initial velocities are the same. So V1 initial and V2 initial are the same. In this case, both velocities are 0, but that doesn't really need to be the number. They could both be moving to the left with a non-zero velocity, and their initial velocity is still the same. They could both be moving to the right with a non-zero velocity, and their initial velocity is still the same. So the point is, we're just going to write that as V initial. Both those can be written as just V initial. Once again, we'll return to this detailed equation and demonstrate what occurs. M1 V1 final plus M2 V2 final equals M1 V1 initial plus M2 V2 initial. Once again, this is called VO. This is called VO because those are the same number, whether it be 0 or 100 or 2, and those will factor out. I'm going to factor them forward because I like to have the velocity on the right. So we'll have M1 plus M2, that whole term being multiplied by VO. So here we have it, M1 V1 final plus M2 V2 final equals M1 plus M2 times VO. And there's our third equation for the day. So if you're approaching a momentum problem, a conservation momentum problem, and you're not sure exactly what to do, refer to this lesson. We have 3 equations for 3 different scenarios. Do they start apart and end apart? Use this equation. Do they start apart and join together? Do they stick together? Then you would use this equation. And finally, do they begin together and separate? Jump to this equation. I won't have these provided for you on quizzes, so make sure you have them organized well in your notes. Submit them on Google Classroom. Oh man, this bothers me that I don't show my explosion. You gotta show something there. So that's about it. If you have questions, let me know. And thanks for watching.